So all of this is joint work with Maria Gillespie, who just introduced me, and Kyle Salois in the background of the Colorado State. Um, so yeah, the goal of this talk is to sort of motivate why this question is interesting to study and hopefully get more people interested in the question and also show some sort of preliminary results in sort of answering this question. So, oops. So let's start by reviewing what a quasisymmetric function is. So a quasisymmetric function over a ring R, and the variables x1, x2, and so on and so forth, is going to be a formal power series of bounded degree such that for any m tuple of positive integers alpha 1 through alpha m, the coefficient of x1 to the alpha 1 times x2 to the alpha 2 and so on is the same as x I1 to the alpha 1, xi2 to the alpha 2, and so on and so forth. For I1 less than I2, and so on and so forth. So for instance, this is an example of a quasi-symmetric function, right? As we have all terms of the form xi times xj to the fourth, where I is less than j, and all of these coefficients are the same. So under sort of normal addition and multiplication, this forms a ring, which we're going to denote Q sim R. And moreover, thinking about this as an R module, there's a basis given by the monomial quasi-symmetric functions, which are indexed by m tuples of positive integers alpha, where we're just summing over xi1 to the alpha 1, xi2 to the alpha 2, and so on and so forth. Okay. So for instance, m21 is given by x1 squared, x2, x1 squared, x3, and so on and so forth. And the previous example is m14. So we'll say that a quasi-symmetric function is symmetric if it's invariant under swapping the indices of its variables. So this forms a subring, which we're going to denote sim R. And moreover, it has a basis, which are a natural basis called monomial symmetric functions, which are indexed by partitions, which are non-decreasing or non-increasing sequence of non or positive integers. And so this little m sub lambda is equal to the sum over all monomial quasi-symmetric functions, where we're summing over all m tuples that can be obtained by rearranging the parts of lambda. But for instance, m, like this capital M12, is an example of something that's not symmetric, right? I have the term x1 times x2 squared, but for instance, there's no x1 squared times x2. But for instance, if we do m12 plus m21, this is symmetric. And moreover, this is the monomial symmetric function m21. Okay. So now let's define what the chromatic quasi-symmetric function. So first, let's start with a labeled graph. So we're going to think of its vertices as the numbers 1 through n. So first, let's just remind ourselves of what a proper coloring is. So this is just a map from our vertices to the positive integers, such that if two vertices are adjacent, they have different, or they're assigned different colors. For each proper coloring, we can define a statistic, which is it's a number of ascents. So this keeps track of the number of edges in our graph, such that the coloring along that edge respects the labeling of the graph. So let's look at an example. So let's consider this path graph on 3 vertices with labeling 1, 3, and 2. So one possible coloring is the coloring 1, 2, 1. And here we see that it has 2 ascents, right? So the first edge, which is colored 1 and 2, matches with the labeling of the graph 1 and 3. And similarly, the other edge, which is colored 2 and 1, respects the ordering 3 and 2. Let's take another coloring. So let's say we now color our graph 2, 1, 2. We see here that for this coloring, there's 0 ascents. And so Shareshian and Wachs defined this chromatic quasisymmetric function, which is just summing over all proper colorings, keeping track of the ascents and the coloring itself using the x variables. So for instance, the chromatic quasisymmetric function for this path graph that we have up above, two terms will, well, one of the terms will be this q squared x1 squared x2, which is coming from this first coloring that we have up here, right? This q term is keeping track of the number of ascents, and then x1 squared x2 is saying that there's two vertices colored 1 and one vertices colored 2. Or for instance, the second coloring that we have contributes 0 ascents, and it has one vertex colored 1 and two vertices colored 2. So some basic properties about the chromatic quasisymmetric function. So when q equals 1, we obtain Stanley's original chromatic symmetric function, which can be used to obtain things like the chromatic polynomial of the graph. Now, for instance, in general, this chromatic quasisymmetric function is not symmetric. So for instance, if we just swap the colors I and I plus 1 in our graph, what happens is that we could break the ascents or the number of ascents of our coloring. But it is quasi-symmetric, right? If we just keep the relative orders of our colorings the same, then it does preserve the number of ascents. And moreover, whether or not it's symmetric sort of depends on the underlying graph and its labeling. So for instance, if we look at this graph that we saw before, this graph 1, 3, 2, and we look at its full chromatic quasi-symmetric function, we get the following, which is not symmetric. For instance, or the reason being that the coefficient of m21, which is q squared, is different than the coefficient of m12. But for instance, if I relabel this graph to be 1, 2, 3, and I look at its chromatic quasi-symmetric function, then we see that the coefficient of m21 and m12 are the same. And this is an example of a chromatic quasi-symmetric function that's symmetric. Additionally, some graphs have like no labeling that give rise to a symmetric CQF or chromatic quasi-symmetric function. For instance, this claw graph, no matter how you assign labels to this graph, you're never going to be able to obtain a symmetric CQF. So a sort of natural question arises, which is, when is the chromatic quasi-symmetric function actually symmetric? Now, there's actually another motivation for studying this question, and this comes from the fact, or from the only two known families that had a symmetric CQF, which were the natural unit interval graphs and naturally labeled cycles. So what were these natural unit interval graphs? We saw them originally or previously in Akita's talk. You can think about these as their vertices are collections of unit intervals on the real line, and the edges correspond to overlapping intervals. And we're just going to label the intervals from left to right, 1 through n. So for instance, let's say that we have these 6 unit intervals. These would correspond to the following graph. So for instance, this vertex 3 is overlapping with this interval 2, 4, and 5. So in the graph, 3 is adjacent to 2, 4, and 5. The other family was this naturally labeled cycle. We say that a cycle is naturally labeled if it's just labeled cyclically. So for instance, if we look at the cycle graph on 4 vertices, this would be a natural labeling of 1, 2, 3, 4. So you can either do it clockwise or counterclockwise. So another motivation for studying this question of symmetry was we have these two families of graphs, and somehow they interacted nicely with this notion of E-positivity. So let's remember what it means to be E-positive. So the elementary symmetric functions form a basis of the symmetric functions. So e to some positive value k is the sum over all distinct or products of distinct k variables. And then E sub lambda is just a product of E lambda 1 times E lambda 2 and so on and so forth. So we say that a symmetric function is E positive if when we express it in our basis, these coefficients in front of these E lambdas are going to be non-negative polynomials in Q. So for instance, this path graph where we have labels 1, 2, and 3, if we express it in terms of the elementary basis, we get the following, which is Q squared plus Q plus 1 times E3 plus Q times E2, 1. And we see that both of these coefficients are non-negative polynomials in Q. So this would be an example of something that's E positive. Or for instance, a cycle graph, when we express it in the elementary basis, is also E positive. So another reason for studying when is the chromatic quasi-symmetric function is symmetric is, well, we have these two families that are known to be symmetric. So these natural unit interval graphs, and so these were conjectured or are conjectured to be E positive by Shareshian and Wachs. And we saw earlier in the day by Hikita that if we plug in any positive value for Q in, then it in fact is E, or it is proven to be E positive. And then for these naturally labeled cycles, Alzi and Wachs also proved that these ones are also E positive. So another motivation for studying this original question that I posed is the following question of whether every CQF that is symmetric is also E positive. Maybe, and we tested this for all labeled graphs with at most 8 vertices, and then for the symmetric families, I think we tested up to 10 vertices. So what are some known results in the literature about when this is symmetric? Well, we already saw two sufficient conditions, which is that our graph is a natural unit interval graph, or our graph is a naturally labeled cycle. Basically, the only other necessary condition that was known is that when we express it in terms of these monomial quasi-symmetric bases, the coefficients form palindromic polynomials. So for instance, if we look at here, this is a palindromic polynomial, which is symmetric around Q squared. And also this one is also symmetric around Q squared. And while working on this project, another result or another necessary condition was given, which is that G cannot be an unnaturally labeled path or a star graph. But this is really all that was known in the sort of the literature. So our question is sort of to expand upon this list. So the first question is, well, if we have a question on all labeled graphs, we sort of want to reduce it to the case of just looking at connected graphs. So the coloring of like disjointed or disjoint graphs don't affect each other. So the chromatic quasi-symmetric function of a disjoint union of graphs should really just be their product. Right? So really this question of whether we can boil or just look at connected graphs boils down to the question of if we have two quasi-symmetric functions that are both not symmetric, can we multiply them to be something that is symmetric? And the answer is no, if we take or no in general. So in other words, if we have two quasi-symmetric functions, and if their product is symmetric, then this can only happen if and only if the two original functions were symmetric themselves. I should say that, or put a little note here, that this is not true if we restrict to a finite number of variables. So there are examples of quasi-symmetric polynomials that are not symmetric, which you can multiply to be a symmetric polynomial. So for instance, x1 cubed times x2, or times x1, x2 cubed is a symmetric polynomial of x1 to the fourth, x2 to the fourth. And so this dichotomy between the sort of functional case and the polynomial case boils down to really the fact that the ring of quasisymmetric functions is a unique factorization domain, while if you restrict to polynomials, it's not. So then, oops. So this implies that the CQF of G is symmetric if and only if the CQF of every connected component of G is symmetric. Okay, so this means that we can really just look at connected components. So now let's look at some necessary conditions. And for this, it's nicer to think about a labeled graph as a directed acyclic graph, where we're going to direct every edge from a smaller label to a larger one, right? Because the only reason why we needed the labeling to begin with was to define this notion of ascents. But if I have a directed edge, we can also similarly define this notion of ascents. Moreover, if we have a directed acyclic graph, then we can always find a labeling that respects the orientations of the directed edges. So we lose no information by thinking about directed acyclic graphs. Moreover, we can view this directed acyclic graph as a poset, right, where a vertex v is less than w if there's a directed path from v to w in our graph. Okay? So in this graph here, these bottom elements are like the minimal elements of our poset, while the top ones are the maximal ones. And in fact, this directed graph here actually gives the Hasse diagram of the poset. So let's look at some necessary conditions. So the first one is that if your CQF is symmetric, then the number of sources and sinks in your graph have to be equal. So remember, a source is vertices with no incoming edges, and sinks are vertices with no outgoing edges. Or in terms of the language of posets, these are the minimal and maximal elements in your poset, respectively. And secondly, the size of any anti-chain in your poset um, has to be at most the number of sources in your graph. So let's look at this example that we showed earlier. So for this graph, we have three sinks and three sources, which is good. But here in our graph, we have four or an anti-chain of size 4. So this means automatically that the chromatic quasi-symmetric function of this graph is not symmetric. And the way to prove this is to find a composition alpha or a tuple of positive integers alpha, such that the coefficient of q to the number of edges m alpha and q to the number of edges m sort of alpha are different. And for this one, it's nice enough that I can describe. So what you do is you take basically a linear extension of all vertices below this anti-chain, then color the vertices in this anti-chain the next color, and then take a linear extension of all vertices above this anti-chain. And so this forms a coloring of your graph where every single edge contributes to the ascents. However, if we think about trying to color this graph, so here we have 4 vertices colored 3. So now let's try to think about coloring this graph where 4 vertices are colored 1. Well, we only have 3 sources, which means that if I want to color 4 vertices with the color 1, that means a non-source vertex is colored 1. But if I have a non-source vertex colored 1, that means that the edge going into this non-source vertex cannot contribute to the ascent number of the entire coloring. Okay, so not every single edge will contribute. So more generally, we showed that if your CQF is symmetric, then your graph has to have exactly 1 source and 1 sink in your graph. So the heart of the proof is the same as before, where we find the composition alpha such that the coefficient of m alpha is different than m sort of alpha. It's a bit more technical, so maybe let me skip this proof. But this theorem is quite strong and implies several several nice facts. So for instance, if your graph is connected and its CQF is symmetric, then it must have a Hamiltonian path labeled 1, 2 through n as a subgraph. So this immediately implies that your graph has a Hamiltonian path in it, or in other words, it's traceable. So let's look at some examples. So for instance, if I look at this bow tie graph, where I've labeled sort of the central vertex 1, this does not have a Hamiltonian path uh, 1 through n as a subgraph, right? So I immediately know that the CQF of this graph is not symmetric. Moreover, this claw graph that we looked at before also cannot have a symmetric CQF, right? Because it doesn't have a Hamiltonian path at all. And so this corollary follows from the following theorem because we have exactly one source and one sink, which is our maximal and minimal elements in our poset. And remember, every antichain is at most the size of the number of sources. So in other words, the largest antichain has size 1. So by Dilworth's theorem, we can cover our poset by a single chain, which gives us this Hamiltonian condition. Moreover, we can use this Hamiltonian condition to classify when a tree is symmetric. But it turns out that a tree is symmetric if and only if it's sort of the naturally labeled path, right? Because every other tree that's not a path graph um, is not traceable or doesn't have this Hamiltonian path. So these were necessary conditions. We also found a new family of graphs outside of these natural unit interval graphs that have a symmetric CQF. And these are called mixed mountain graphs. So for us, a K mountain is going to be a complete graph on K vertices. And then a K plus 1 bottomless mountain is going to be a complete graph on K plus 1 vertices with one edge removed. So for instance, this is a 4 mountain, which is really just K4. And then a 5 bottomless mountain is just K5 with one edge removed. So a PKM mixed mountain graph is a string of P mountains or bottomless mountains, or I should say a string of K mountains or K plus 1 bottomless mountains, where we have exactly M K mountains and P minus 1 or P minus M K plus 1 bottomless mountains. And we're going to join adjacent mountains by a single vertex, and then we're going to join the first and last vertices of our mountains by an edge. Okay. So for instance, this is an example of a 5, 4, 2 mixed mountain graph. So it's 5 because we have 5 mountains. It's 4 because all of our mountains are either a K4 or a K5 with one edge removed. And then we have exactly 2 K4s in our graph. So just to make sure this concept is solidified, right? So you're allowed to have only K mountains or K plus 1 bottomless mountains in your graph, right? So we could have like all K3s, or we could have like all K4s with one edge removed. But we're not allowed to mix cliques of different sizes. So for instance, I can't have a clique of size 3 and a clique of size 4, and then connect them. So this is not an example of a mixed mountain graph. And similarly, I can't mix a clique of size 3 and a bottomless clique of size 5. Okay, so it has to be this special relationship of having a K mountain and a K plus 1 bottomless mountain. Moreover, note that this family of graphs generalizes the cycle graphs, because if I take like K2s and then string them together and then join their ends, this is an example of a cycle. Okay. So we also need to label this graph. We're just going to label them from left to right, or if you're thinking about them as a directed acyclic graph, we're just going to direct all edges from left to right. Okay. So the first thing that you might notice is that in my description, I haven't sort of specified where along the chain are the K mountains and the K plus one mountains. So it turns out from the perspective of the chromatic quasisymmetric function, this actually doesn't matter. So in other words, if we have the same number of K mountains and K plus one bottomless mountains, then their chromatic quasisymmetric functions are the same. And essentially the reason is that if you have like a K mountain and a K plus one bottomless mountain right next to each other, we have this map that allows us to swap these two maps, which is ascent and weight preserving. And note that this map also works in the case of natural unit interval graphs. In other words, if you have a K mountain and a K plus one bottomless mountain in the natural unit interval graph, this map that we defined also works where we can swap them. So the position of the K mountains and the K plus one bottomless mountains doesn't matter. Okay? So then we show that this family of mixed mountain graphs gives rise to a symmetric chromatic quasi-symmetric function. So this is an entirely new family of graphs that are known to have a symmetric CQF. Um, and uh, given our question earlier about e-positivity, it's sort of a natural question to ask whether these things are e-positive. And in fact, we conjecture that they are. So for instance, if I look at this graph here of three mountains stitched together, and we look at its coefficients in the elementary basis, we see that it is also e-positive. So we're currently working on proving that this family is indeed e-positive. Moreover, up to 8 vertices, so we looked over all graphs or all labeled graphs up to 8 vertices. It turns out that the only families of graphs with a symmetric CQF are natural unit interval graphs. And this new family of graphs, which are these mixed mountain graphs. So it's sort of a natural question of whether these are the only two families or are there possibly more.
Okay, let's thank Joseph. So there were a couple questions in the chat, and I answered some of them. Are there more questions? Or Joseph, if you want to see the chat and see if you want to add anything. And also anybody can raise their hand or ask a question.
Hi there. I have a question. Thanks for the nice talk.
Hmm?
So this is very simple-minded, but you can also ask these questions without the Q, right? I mean, you can just ask about this chromatic symmetric functions.
Well,
No, does it not make sense without a? Oh, I see. Okay.
yeah. But what you can do is LZ defined, so you don't really need a labeled graph. It's really, you could just define it on any directed graph. And so sort of the natural questions still hold of like when this is symmetric. And so for these families, as Per said in I think his comment, it's known that these circular unit interval graphs are known to be symmetric. And it would be like an interesting question of if you have if your CQF is symmetric in this general setting and you have a directed cycle, must you also have a Hamiltonian cycle? That would also be interesting. Sort of an analog of our Hamiltonian path condition.
There's also one more question in the chat from Per, very relevant to, so if you want to answer it, Joseph. It says, well, maybe I should read it aloud. So if you do a plethism to make LLTs, to make into LLTs, do you get something interesting? There's the QSIM chromatic to unicellular LLT correspondence.
Yeah, so it's sort of interesting. Okay, so it doesn't seem like there's this nice bridge between the plethism and of these LLPs and these chromatic ones. But what you can do is like one way of thinking about these LLT or unicellular LLTs is to think about them as like summing over all colorings, not just proper ones, but all colorings in your graph. And then, so you can do the same thing where you look at it for these mixed mountain ones, and it turns out that this analog of LLT for these mixed mountain graphs is also symmetric. And if you shift them by q+1, like you did in a previous paper, it still seems to be E positive or conjecturally. But yeah, it doesn't seem like there's this nice bridge.
Yeah.